All right. Hello, everyone. And we're back with another day of WASI Preview2 walkthrough, more APIs. So yesterday we did WASI clocks and WASI random. Today, following the outline we had yesterday, we're going to do WASI IO, which is all about streams, and WASI poll. And we'll probably get started on WASI file system because there's a lot of space there we got to cover. And we only have one more day scheduled. If we run out of time, we'll schedule some more live streaming episodes, but today we'll see how far we get. All right, so let me check out the chat. If everyone could just confirm that you can hear me somewhere in the chat, just let me know. Yesterday I got started and I forgot to click the actual button that says start the stream. For about 10 minutes, I just talked about myself the whole time. So if people could say that you can hear me, that'd be great. I'm getting some waves in the chat. That's good. All right, so assuming that we are actually here, there we go. Let's dive right into it. Let's go to the screen here, and we're going to pull up an editor. I'm going to go to WASI IO on the main branch, and we're going to edit the README of this repository. Actually, for this one, I actually think this will make more sense to go straight into the wit.md file. Because I think with streaming, I think it's actually going to be useful to talk about what this is, and then we'll talk about the README and how to summarize what this is in the README. So WASI IO is this kind of concept that actually evolved a bit. We had this early idea early on with WASI that we knew that the concept of streaming would be really important to WASI. It's really important to lots of different platforms. You can look at Unix, you can look at HTTP, you can look at lots of different systems that are going to build up on top of those things that have a concept of streams. And streams are really valuable for composing multiple pieces of systems together. Like this has already been demonstrated in a lot of systems. So we knew that streams are going to be a super key thing that we want to have. But early on in kind of WASI's lifetime, it wasn't really clear what should a stream be. Should a stream be a file, like Unix has everything is a file concept of a stream, or should a stream be something more like a channel in some of the languages, or what should this thing be? Should it built into language? Is it a handle? Is it a type? And so we kind of fished around for a bit. And early on, we had this thing called WASI IO, an earlier version of WASI IO, where we sort of introduced the concept of a stream as a library. And it's kind of envisioned to use handles and kind of sort of this first-class handles and a thing that you can either read to or read from or write to. But then pretty quickly, we recognized that when you want to start generating bindings for streams in source languages, you want to have streams, and a lot of source languages have their own concept of a stream already. They have a concept of a thing you can read and write from, and it looks different in different languages. But a lot of languages have this concept, either a stream or sometimes an iterator is kind of another way of representing a stream. And we kind of know that this is a really valuable concept to have, and a lot of source languages already have existing concepts. And we'd like to have bindings that can hook up the streams that we have in WASI that we'll use to compose many things together with the source language streams. We want those to be sort of a native integration. And really the way to get there is to put streams in the IDL as a type, just to build it in so the IDL has a concept of a stream, because they really are that fundamental. And then the binding generators can then take that and say, okay, I know I have a function that has a stream being passed in or a stream being returned out. And so I can now generate bindings in all the source languages that use those source languages' native stream abstractions in some form. So then what happened was we sort of abandoned WASI IO for a while because we're saying, okay, let's focus on building stream into the IDL. And then just as additional backgrounds, these ideas also kind of existed alongside a set of ideas about async. And how to make the component model address async, which is actually a super important topic that I think will be very valuable to WASI as it grows, is having a good async model. And it became clear that we really wanted to have streams and async be integrated, because that allows us to do, if one component is talking to another component over a stream, we can have a single event loop that can kind of monitor both and kind of schedule tasks across both. We can have streams running on both. So async happened, and sort of we decided that the basic stream abstraction should be an async thing. But then that left us kind of an awkward place, because now the situation with the component model is that async is going to take a little bit longer to develop. It's not in the component model repository yet. And there's some designs out there. There are a lot of interesting things that are in the sort of like set of ideas of what we think this model, it should look like. But there's a lot to figure out. Making async work and work well across languages, and many source languages at this point have a native concept of async, whether it's Go, Python, Rust, C#, JavaScript. Like lots of languages have a built-in async concept, and we want the async that we build into WASI to be able to play nicely with all these languages' async models. And we want this thing to be scalable, and we want this thing to be safe, and we want a lot of things with the async model. And I think we can do it, but it's going to take a little bit more time to build the standards and the tooling and all the stuff to make sure that really works really well. And so now what we're doing with WASI.io is we're kind of making a full circle and saying, okay, right now in this moment of time, there's actually a lot of value in having a version of WASI that's out there, that's built on WIT, but that doesn't necessarily block on having a full finished async model. And so like we're bringing back WASI.io and saying, let's bring back this idea of a library-based stream that's going to be based on resources. So it's not going to be async in this iteration. It's not going to be another idea with streams. Another advantage of building streams into the IDL is that we can make them typed streams. So byte streams are obviously a really common use case, but there's actually a lot of cool things you can do if you can say that these streams aren't just streams of bytes, but could be streams of any type T. And so then when you can stream typed objects between components, that's a really, really powerful way of composing things together. And so that will be possible here because the IDL doesn't have full type generics. So we're going to just focus on byte streams. We're going to focus on synchronous I/O for now, with the idea that in the future, the component model will add async and we'll add fully async streams, and we'll be able to convert everything from these streams to the built-in streams in the future. That's kind of the background of what this is. So we're sort of bringing back WASI.io and bringing back I/O streams. One additional bit of background, WASI.io originally included the concept of I/O arrays, which I think is a nice abstraction for, if you think about the concept of what a file is. A file is, at some level, an array of bytes. And you can think of that more abstractly as just being like an array that lives on the outside of a program that maybe can be accessed by multiple things. And it's kind of nice to think about that way because it sort of separates it from file semantics, which kind of has a lot of baggage. There's kind of a lot of baggage between what people expect a file to be and what a file is on actual operating systems like Windows and Unix platforms. And so an I/O array was kind of this abstraction that kind of tried to abstract over that and give you a generic array that could be a file, or it could be a buffered memory, or it could be a block device. There's actually a number of different devices that there's implementations of the kind of I/O array concept that we have out there. But at this moment in time, I/O arrays don't have quite as compelling use cases. Streams really are the big thing to focus on right now. So focusing on streams, and we're going to leave I/O arrays until we have more use cases motivating that. All right, so with that background, let's take a look at our wasio.wit file. So yesterday I started doing a few things with like, we're migrating away from resources in the WIT files at this moment because WIT files aren't in the tooling yet. That's going to be a temporary thing. We'll migrate back to resources as soon as the WIT tooling has more resources. And so today in the stream, I'm not going to do any of that. I think I'm going to correct that mistake. I'm just going to leave the resources as they are, leave things in that form that they're in. We may yet make another pass of these to check in versions of these that take out resources and just use the U32 indices into an applied global table as a temporary thing. But one kind of nice thing about this situation is that we can, for the most part, ignore these differences at this level. So what we're focusing on today is just really the semantics and the feature set of streams. Like, what is a stream? What can you do with a stream? What are the operations you can do with a stream? And then the question of like, how do you identify a stream? Is it a handle, or is it an index into a table, and this will sort of apply with the future built-in streams as well. It'll sort of be like stream is just a stream, and you can talk about it as a handle or an index to a table or a built-in thing. But then fundamentally, the set of things you can do with it is basically the same, so they should be largely interchangeable at that level. And so the documentation we'll write today will focus on kind of that interchangeable level of like the common functionality that ties all these things together. So WASI.io is an I/O abstraction API that focuses on providing stream types. In the future, the component model is expected to provide built-in stream types. When it does, they're expected to subsume this API. So that's sort of the short version of what I just talked about. The very first thing in this file is this stream error type. Right now, it's a record with no fields in it. This is something that might evolve over time. And so this is the stream error is this thing you get from, well, I guess we'll see later on, like read and write, the basic things you can do with streams. They either succeed and give you the data, or they fail and they give you a stream error in the error case. And it's an interesting question. What should the error type for a stream, a fully generic stream, be? So with a fully generic stream, we know that it's not a file, or it might be backed by a file, but the consumer of the stream or the producer of the stream should be abstracted away from any kind of knowledge that it is a file. So there's no fsync operation, there's no seek operation. It's just like you're just streaming. It's just reading bytes or elements eventually, or you're writing bytes or elements. And there's kind of no concept of being able to peek past the stream abstraction to see the underlying file and to look at things like fstat or other like file properties. And so since we're kind of hiding like what this thing is, that means that this stream could easily just as well be a stream to a socket or a stream to a pipe or a character device or an SSH channel or an HTTP connection. And so the question is, if we have this fully generic stream concept that could be any number of these different things, and the idea is that consumers shouldn't have to know where the stream is coming from because we won't be able to pipe things in from any source and have it work. How should we report errors? What kind of errors can happen that don't require the consumer to know what it was? And so right now, kind of the idea is maybe streams can only fail in one way. And so we only have like what POSIX would call EIO. An IO error happened. I don't know what it was. I can't tell you anything about it because that would require me to tell you what the underlying thing was. And so it's just a fully generic error. So that may evolve over time, but that's kind of the current thinking of what's going on with the stream error type. Is it's just like this it's an error happened. You know that if you're doing a read, the stream failed, maybe it disconnected, maybe the file had an error, a disk error or something like that in hardware. If you're writing, maybe you ran out of disk space, but those kind of things require you to know about the underlying device, and we want to abstract that away. So right now, the stream error doesn't have any information. We'll see in the future if that evolves, but that's the current thinking of that. So with that, we can launch into the very first resource type, which is input stream. And so I can point out here that we're separating output stream from input stream. There's going to be separate types, and we don't have a bidirectional stream. If you want to do bidirectional I/O, the way to do it in this API is to have two streams, one input and one output, and just keep them together as a pair. It's kind of interesting to look at the Unix design, where Unix has some things are pairs if you want to do bidirectional, and some things are like a single file descriptor can do both. So if you have a socket can do both read and write. It's sort of this bidirectional thing. But if you have a pipe is just one direction. And then you have things like standard in and standard out being passed to main, and those are file descriptors, and you might be able to read and write, like you can write to standard in if it happens to be a file in some weird cases. But the basic idea of how you're supposed to use them is that you have input and output are separate handles, not sort of one handle that can do both. And so this is kind of like looking more like the standard in, standard out, where you have separate handles, or like pipes where you can have separate pipes, rather than sockets where there's like one thing that can do both. And actually, we'll talk about how you can use input stream and output stream with sockets when we get to the WASI sockets proposal. It's at the end of the list of our thing to do in the stream. So input stream is going to be input, and the thing you can do with it, the main thing you do with it is read. And so right now we're just focusing on bytes. Read can read bytes from a stream. See, would WASI I/O be compatible with future async component model, or will it be deprecated then? So that's a good question. I think people I've been talking with people, in fact, just within the last several days about this, about like what would the plan be for this kind of migration. And I think what's an idea that's kind of been catching on has been that we would leave this WASI I/O stream concept in place. We're not going to sort of take it away so that existing code can still work, but that we would eventually, add new APIs that would be alongside them that would use WASI streams, and then over time, WASI I/O would sort of disappear. All right, and what is the bool in this tuple? That's a great question, and I should document that. So the bool here is the end of file indication. And so you're doing a read, and you get a tuple of the list of U8, the actual bytes that you just read, and the bool indicating whether or not you just hit the end of the stream. End of file, end of the socket closed, end of a pipe. Almost all input streams that you can read from have a concept of an end. And so this bool tells you whether you've reached the end or not. Returns along with a bool indicating whether the end of the stream was reached. So we can point out that this actually differs a little bit from kind of the POSIX way of doing things, where in POSIX, you have a read function that can read from a streamy-like thing. And in POSIX, the way this works is you have the read can return 0 bytes. And it's sort of the special case that when read returns 0 bytes, then that's understood to mean the end of the stream has been reached. All right. We're going to give you an explicit thing. And that's actually, it's kind of a nice sort of orthogonal property that we don't have to have this special case, because sometimes when you do a read, it needs to return early because it gets interrupted for various reasons. And so we don't have to worry about having a special case saying, like, if we get interrupted before any bytes happen, we just have to know that we got a short read and we have to keep reading if we want to get bytes. But if we get this bool telling us at the end of the stream, then we know that it's over. We don't ever have to call read again to figure out if that was the end of the stream or just we happen to get 0. All right, so that's the bool thing. So you call read, you give it a length of how many bytes you want to read. Another thing I could point out here while I'm going through is that the length here is a U64. That also subtly differs from how POSIX does read. In POSIX, when you call read, you pass it a length, which is a size t, I think, or maybe it's an S size t. No, it's a size t. So it's unsigned, but it's a size which corresponds to the size of the address space. And in POSIX, that makes sense because the size, you can't read more than would fit in your process address space because you have to pass it a buffer which lives in your address space. But we're using U64 here, partly because we're kind of thinking ahead to WASM64 kind of situations. In WASM64, you'll be able to read 64-bit potentially buffers that are larger than 4 gigabytes. And also, as WASM grows beyond just linear memory-based languages into GC languages and potentially other languages in the future, it won't always be limited by a linear memory concept and having a size t kind of concept. Languages will have just a GC array, and you can read into whatever size GC memory you have. And so U64 kind of just gives you it's a single API. We don't have to worry about the API being different for different kind of configurations of WASM32, WASM64, or WASM GC, or other kinds of WASM. There's just one API that works the same way. And if you try to read more than can fit in your address space, then probably what will happen is you'll just get a short read. That's worth mentioning in the documentation here. I want to talk about it. Callers won't be able to accept. Maybe I'll just say more generically. Some callers have limits in how much data they can accept in a single call. For example, WASM using linear memory with indices. Let's see. This is actually an interesting question of how are we going to communicate to the other side. This may be a bug, or at least something that we need to sort of think more about in the component model, because the other side, the callee, will know what the caller's limitations are, and so it may try to return more data than the caller can accept. So let's make this a to-do, or maybe fix me. We'll go all the way to fix me. The len here is U64, have limits in how much data it accepts. Yeah, using hackmd here, I don't have language sensitivity, so I'm like manually hacking on comments here. Okay. How should we arrange this? Okay, so that's actually a question that I'm just feeling now that we need to think more about is if the caller can't accept more than a certain amount of memory, how would the callee know this? And I guess the way this would show up, if we just naively do this as it's written right here, is that this would work as the callee would try to call the caller's components allocation function to allocate the list. And if you pass that function size that's too big, it will fail. And then I guess the callee can know that, and it could fail here. But we still should think this through, because there's potentially a sort of interaction here of when it does fail, do you want it to fail and just have the read call fail, or do we want to have it sort of fall back to like, well, we'll give you the biggest buffer we can. But then how big should that be? That's like, what if you try to read, and even if in WASM32, you might not be able to allocate the full 4 gigabytes. So like, what if you try to read and we can't allocate the whole buffer? Maybe that's okay then. Actually, so you're watching me like brainstorm the design here live here. So this is uncharted territory. I don't think there are any answers to this yet. So we're just figuring this out on the fly. So I'm actually thinking about this. Maybe this really becomes the responsibility of the caller that the caller should not pass in a length that it doesn't think it should be able to allocate. So more specifically, if the caller is a WASM32 using program using a 32-bit len memory, and the caller shouldn't pass in a length which is more than 2 to the 32. And it probably shouldn't even pass in a length which is more than like 2 to the 31 or even close to there, because it probably can't allocate a contiguous buffer that big. Most WASM programs have other things going on in a memory, so they can't afford to dedicate the entire memory to a buffer. So probably can't even do 4 gigabytes. It probably has to do something smaller within the range of what it could actually allocate. I think that seems reasonable. So I think actually we need to go back on this, but I'm going to need to have more time to think about what exactly we need to say here. Okay, now I'm thinking about more. Maybe we just do this. Length here is used for. Okay, I got to do this later. I'm going back and forth on this. I think I'm going to do this later. Okay, so we'll revisit that. That's an interesting side question we'll have to figure out. So the skip function is just like read, except instead of giving you the actual bytes, it just skips the bytes ahead into the stream. So we're just going to read the bytes and discard them. And this has a kind of nice property that if you know that you don't care about some number of bytes coming in, this avoids ever copying those bytes into the instance. So I'm going to write, this is similar to the stream type, or the read function. Avoids copying the bytes into the instance. People sometimes talk about zero copy as being an important property of a system. And the Kubota model has an answer for zero copy. It has like several different answers for zero copy. And this actually is kind of part of one small part of one of the answers. And so the answer is like, if you know there's data you don't need, don't copy it. And so that's kind of one way of achieving zero copy in a very particular way. So skip is kind of one way of doing that. It won't always be useful, but it does kind of correspond to, like, if you're reading a file in Unix, you can use lseek to skip forward and avoid reading bytes. Skip is kind of the same thing, way of doing that, except that in Unix, lseek only works on files, where in the Kubota model, skip will work on any kind of stream, whether it's a file or a socket or anything else. You can always skip ahead. And that's it. So that's it for input stream. It just has read and skip, and that's all it can do. And it has the same usage for length, it has the same tuple, except this time, instead of giving you the bytes, it's going to give you usage for telling you how many bytes it actually skipped, which could be less than what you asked for. And in fact, I should mention that as well in the read function. Okay, so we're going to say a similar thing for the skip function, so that number of bytes skipped along with a bool Okay, so that is the skip function. So now we have output stream, which is sort of obvious. But I think eventually I'm going to want to have documentation for these types, but I'm going to leave that for now. I think it's fairly obvious. Write bytes to a stream. To document the return value at the very least. Okay, so like read, buff could also write fewer bytes than are requested. So this is a familiar concept from POSIX where read and write can also be interrupted early and do fewer than requested. So read and write are relatively low-level things that will often be used within the concept of a language standard library, like a libc or other standard library, which will take care of these things for you. So you call printf, and you don't have to worry about printf not printing the whole thing. It will do a loop and call write for you. So we have the write function is data to write. It returns the number of bytes written, and of course on error, it has this stream error type. All right. So on the writing case, we actually include, in addition to write, in the read case we had read, and the one extra goodie was skip. In the write case, we have a number of extra goodies here. So write repeated is a way, another one of these small pieces of the zero copy IO story is if you know you're going to write, for example, zeros, a stream of zeros that has a number of zeros in a row, you can tell it to do write repeated. And then this will write a single byte multiple times to a stream without ever having to have a single buffer containing that byte written out many times. So this is sort of zero copy because you're not actually copying the actual data out of your memory into the outside. You're basically describing a formula by which the outside can derive the data that you want it to have. So I think in the bytes case, the only really interesting use case for this is like writing out zeros. And it's kind of fun because this also kind of gives us the ability to expose the concept of holes in files. So in POSIX, you have this kind of concept that files can be sparse. They can have holes in them in the allocation. And the way you create a hole in POSIX is you have to do this sort of tricky dance with, you use lseek to seek past the end of the file, and then right there, and then POSIX guarantees you that semantically, it's as if you sort of filled in that gap with zeros. So what we can say here is that the abstraction is just what you really want to do is just tell the system, I want you to write zeros. And then the implementation, if it knows it's talking to a file, could create a hole for you because it knows you said, I want to write zeros. The implementation could just seek ahead and create zeros using write repeated. So this allows us to create holes in the implementation if you want to, but it also keeps the abstraction sort of independent from being aware of files, independent of having a concept of a seek built into the stream. So okay, so we're going to write that stream there. All right, then finally we have a splice function, which is a way to say, I want to read from a stream and take the data and immediately write it to another stream. This is another kind of a way to do a zero copy IO in a limited way, which is to say that if you're doing a splice, we're reading from this input stream and we don't ever copy the data into the instance and then back out into something else. We can actually tell the implementation to do straight copying from the source to the destination. And this should allow implementations to do things like in Linux, there's some special APIs. There's actually a set of APIs called Splice, VM Splice, but also copy file, I believe, or what's the API called? I'm drawing a blank on what the name of that function is for Linux, but we'll be able to basically have APIs which can read from one file descriptor and write to another without copying the data into the process and out of the process. So we can use those APIs, and that's kind of a form of zero copy because now we're not copying it in. That also means if you have a chain of things, of like a bunch of different components are chained together with pipes, we can have one producing data, and if the ones in the middle know that there's a sequence of data that they're not going to touch, they can just like forward it on, and we can forward it directly from one to the next to the next to the next without doing any copying along the way. You can just splice it all the way from one to the other. So that's a nice optimization to have, and I need to say more about it. So we're going to say that the source. Okay, I'm getting behind on my questions here too. The chat delay is pretty long. Okay, yeah, I've not seen the chat questions right away, but partly it's because I'm looking at my editor window and not at the chats. Let's see. Is it a considered? Let me go through the questions here before I do run on. So, is it considered a stream error when read is called after the end of the stream? Yes. So that's a good question. I should document that. I think my idea here is that once a stream ends, it would just continue to end. There are use cases in, for example, Unix streams where you hit the end of the file, but you want to be able to keep reading because you're doing something like tail-f. You want to just keep reading to say like someone else might append. And if I keep reading, eventually I'll see it. I think what we want to do here is okay. The other questions, that's great. So let's stop and do questions here for a minute then. So I think what we want to say is if you have a use case which is like the tail-f use case, what we really want to have is a way to tell the libc what you're doing. That you don't just want to have a single stream and that you want to keep reading from once it hits the end of the file and keep reading from it. You want to be able to tell the libc that you're actually deliberately doing a read from a file that you know might end. And if the libc and if the libc knows that, or the other language library knows that, it can actually provide, you can use a different sequence of WASI calls. I think when we get to the WASI file system APIs later on, we'll see what the mapping from files to streams actually is. And I think we can talk about the tail-f use case there. Let me make a note to talk about tail-f, or any kind of use case where like you're monitoring a log file and you want to see what happens in a log. So you're always doing reads and you're expecting to hit the end of the file many times. If we tell the system that's what we're doing, then the system can make that work. And it won't give you an end of stream. It'll just tell you there's nothing there right now. And you can just tell it that, don't give me end of stream, just let me keep reading. Tail-f. So we'll address that in a little bit different way. And that means I need to go back and document end of stream here. Once a stream has reached the end, once a stream has reached the end, subsequent calls to read or skip will always report end of stream rather than producing more data. So let's put that in the skip function too. Okay. Provide a len range, let's see. So yeah, the U64, I think that's an interesting question. I think I managed to convince myself on the fly here that it's the caller's responsibility to not pass in a U64 that's too big for itself. And I think in general, you're not going to want to do a read with like a multiple gigabyte buffer. I think that's probably way bigger than almost any use case would actually want to read in a single call to read. That typically you'll have a buffer which is much smaller than that, and that'll be big enough to do the kind of buffering that will amortize over any IO that you care about. So I think in practice, I think we'll say is that the caller should just not use, excessively large buffers that are larger than they themselves can allocate. And if you somehow do, then it'll fail. I guess the question is just how do we fail with that? Is it a trap, or do we just give you a stream error? And that's something that I don't know off the top of my head what the best answer is there. That'll be what we'll have to figure out. The WASI runtime could conveniently chunk the data, perhaps. When requested massive amounts of RAM. Yeah. So that's kind of another option, is like if we request too much, then the runtime could like scale it back and give you something that fits. But that kind of feels like it requires a bit of cleverness, and it's kind of this weird two-directional communication where like you're telling the runtime, I want this much data, and the runtime says, okay, I have this much data. How much can you accept? And then you can't accept that much. So it has to go back to the runtime to say, okay, now that you can't accept that much, I'll send you less, and then you can accept it. So it's like this back and forth kind of communication, which feels pretty awkward. So I think we want to kind of avoid that. And I think it's not going to be a common use case. I think we could just say like the common use case should be, use a buffer that's more like megabytes, kilobytes or megabytes in size, and not gigabytes in size. And you're probably in a good place. It's probably a good idea anyway, because that would be an excessively large buffer to read all at once. All right. Can shared memory be used by WASI instances to avoid zero copy? And so in the component model, the idea is that your linear memory, we don't want to share that, because that would require describing things like the lifetime. Eventually, when we have threads, it'll require describing things like what's the synchronization policy of that memory. And it'll require conventions like what's the encoding and layout of data in that memory. And so the component model is built on what we call shared nothing, where the memory itself is not shared. But there are ways to share memory. And the main way we can envision doing that is with resources. So resources are just references to what could eventually just be objects in linear memory. But the difference between resources in memory and like literal shared buffers in linear memory is that resources, all access to resources goes through APIs. you have a function call to access this thing instead of just a direct load and store. That's important for the capability model. It makes sure that everyday access to the actual data is refusable. But if you think about like optimization at runtime, if the host sees that after you've linked everything together, you're calling these APIs and they're just reading data and writing data, then potentially they could be inline. So they could those calls could essentially be inline and be as cheap as a direct load and store in the optimized case. So the big caveat there, though, is that resources, when you access a resource, you get a handle, and that will look to a program like a file descriptor, and you can read and write with that file descriptor, but you can't, at least today, there's not going to be any way to map that file descriptor into your linear memory. So you can't use your own language native like raw pointers to point at that data. It's always going to have to go through that file descriptor. That's actually something that people are talking about potentially changing at some point. There's an idea that like, what if we added like a blob resource, which would be a thing you get a handle to, but then maybe there'd be a function you could call in that handle that would say, semantically, copy the data from this blob into my linear memory. But then, like, if we build that into the language, the implementation could work by like literally mapping the data from the blob into the linear memory. Then you could use raw pointers directly to talk to it. We would map it with like private, so that you still wouldn't have kind of a shared like I can mutate this thing and someone else can see me mutating it situation. But we might be able to pull off like mapping incoming data, like essentially read only into your address space with zero copy. That's kind of another way we can do a zero copy situation. That doesn't exist yet today, but that's something that people are talking about. It's like another way of like, taking resources, which are one of our big zero copy techniques, and mapping them into the address space to give you that. And then potentially in the future, another iteration of this could be like, if you want to have read write, you could say there's an operation to copy the data in, where a copy is a semantic copy and not necessarily a literal copy because it could be an map. There could be another function which says copy the data out. So any plan for mmap? I'm seeing the question now. And so this is kind of what I'm talking about. I think my guess is that WASM won't have a literal like Unix mmap. But what we can do, because the actual mmap actually has like 6 or 7 different like distinct things that it gets used for. And I think what we might end up doing is kind of like splitting out those different things into different functions and giving you access to the different pieces that are in a somewhat more specialized way, but in a way that doesn't kind of compromise the overall composability and security of the system. And so one of the things you can do with mmap is I want to read data. And I want to read data by mapping into my address space. And so that's a thing where we could have a resource and you get a handle of the resource and you could say, map the data in this handle into my address space. It's just bytes. So map it to my address space. And that could be done in the implementation with an mmap, and you get the performance characteristic of an mmap. And one nice thing about doing that is that an engine that doesn't have an mmap, if you're running on a platform that doesn't have the ability to do an mmap, could semantically just do an actual copy. And you could run the code, it's just that you'd have to do a copy. So like, we'll get an mmap if you can, but we'll do a copy if we can't. It's kind of the situation there. And then I think that the step beyond that could be like, what if there's an mmap for a copy out? So I have this data in my address space, and I want to call this function and say, copy this data from my address space back into the blob, or probably not a blob, because we typically think of blobs as being immutable. But if we have some kind of resource that you could write to and say, I want to take this data that I mapped it into my address space. I did a bunch of writing, and it probably mapped in with like a copy and write thing. So I have my own copy. But now I want to take this data and I want to flush it back out to the resource. And potentially I have a function to do that too. And so those kind of things are like, there's a way you could imagine doing that in a way that would kind of give you a zero copy overall situation. So it's not going to be like you just do an mmap and now you get reads and writes that might be directly modifying an underlying file. But we can do a thing where you mmap it in, do reads and writes, and then you tell the system, okay, now I'm done writing. Now go ahead and flush it out. And that'll give us kind of the semantic tools to preserve the composability of the system and not have to worry about all the exposing kind of the chaos of sort of mmap and asynchronous bytes just showing up in files. Okay, working through the questions still here. Write repeated really makes sense for streams. Use case seems for regular files instead of streams. So that's an interesting question. So what's the difference between a use case for a regular file that's not a use case for a stream? I think write repeated in this iteration isn't going to be hugely useful. It's not going to be this thing that people use all the time. I think there might be some use cases where you can imagine doing a write of 0, read of length 0. So I'm just also kind of watching the questions come in every time. So if you do a read of length 0, that's just going to return immediately. It's going to say, I want to read 0 bytes, and so that will just succeed immediately. I think that's kind of it just kind of collapses into nothing useful. There is not an ability to say read all. That's not going to exist in this design. You're going to have to tell it a maximum every time you want to read. There's a maximum how much you can read from. So getting back to write repeated, sorry. I think writing zeros is a thing that some use cases need to do. I don't know how common it'll be. I think write repeated gets more interesting when we think about the future of streams being typed streams, where we can have streams of records, and you want to send, you're sending structured data over a stream. I think that's a use case where we'll see more things for write repeated, and we'll see where that goes. So I think it's a thing that's it's easy to implement. It's not that much harder to add to the system right now, and I think there are some use cases for it. And there is this fun idea that write repeated maps to holes in sparse files in Unix. Yes, okay, I'll get down to there. I'm going to work through the questions in order. I have a tendency to like jump ahead to the thing that's happening right now, but I'm trying to work in order here. What about these case of splice, where you don't know the length, but you want the full stream to be piped? Do you provide a max len number that can represent it? Yeah, so the actual the built-in stream type, there's a concept of there's a function called forward, which says I want you to take this stream and forward the entire thing to this other stream. I think that makes sense, but I think it's a little bit awkward for the synchronous model. In the async world, I think that makes sense because that forward function can itself be async. But in a synchronous case, if you call that forward function, it would essentially block until the entire stream has been consumed, the entire output stream has been consumed. Which, maybe that's okay. I'm actually thinking this right now and thinking that maybe we can just add a forward function here. Splice stream. Repeated splice. In fact, this doesn't need to be called splice stream. When we have resources, we don't need to append stream to all the names because it's methods essentially. So let's add forward function. This is the great thing about doing this right now is we can just like add stuff, and as long as we think it makes sense, it's super easy to add things right now. It'll be harder to just add things this easily in the future. So this is the great time to do this. Okay, so this is where you're supposed to say, I want to copy the whole thing. I'm not ever going to touch these bytes again myself. I want to forward the whole thing over, and don't bother me with having to do like this loop of splicing. And that can actually be kind of nice because then you could basically say, well, okay, then do we want this to block? If you call this thing, do we want it to block and wait for the stream to complete? Or do we want to say that this somehow magically, hooks up the input to the output, and then the caller can keep running? That's the tricky part. I don't know the answer to that. That's a good question. So what should we do there? I think the splice kind of gives us an answer to that. If you use splice, you sort of imagine the use case of like, I want to copy the entire input stream to an output stream. You just have a loop, and you call splice repeatedly. And that means you're basically committed to blocking until that stream is consumed and that everything is copied over. With forward, we could do the same thing. It's a little bit more convenient than having to write a loop. Yeah, I think we're just going to say it's going to block. And then also kind of that makes it sort of like is it worth having this function if it's just going to block? Because it's just like a convenience wrapper around splice. Maybe it is, because maybe this allows the implementation to say, like, in splice you have to pick the number of how many bytes you want to do each time. And if you just want to say copy the entire stream over, I guess there you could literally just pass U64 max and say, like, maximum number of bytes, splice it over, and have it copy. I like how forward gives it kind of more of the intent of, like, I want to copy the entire thing over, and you, the implementation, can pick the most efficient way to make that happen. Like how big the buffer should be, don't stop. If I give you a number that, like, the length is too small, don't stop there. If I give you a number that's too big, don't try to overexert yourself. Well, you wouldn't have to, though, because the splice is not guaranteed to be atomic in terms of the underlying, like, a file read and write. And so if you give it U64 max, there's no reason why the implementation would have to go and do that entire thing as a single read. It wouldn't even have to try. So I'm kind of on the fence about this. I actually don't know if forward is a good idea. Common use case is forward more than splice. You're probably right. I think if you look at a use case here is the Rust standard library, where we have like the copy function. And here you say, like, I want to copy from this read to this write. It's kind of a pretty common use case. And it's basically like the forward use case. Except what we can do here is that reader and writer in Rust can be, they can be special adapters that can say, like, I'm only going to read like a limited number of read. I'm only going to write to a limited part of the output stream. So you can sort of adapt these things to make a copy be a limited copy. So I'm not sure. I think yeah, okay. I think it's enough to put forward in there. If there's objections to it because people say it's not necessary, then we'll deal with that. Part of the process here, actually, this is a good talk about this. Part of the process here is that we can just make arbitrary changes right now. I'm just like throwing stuff in there and making changes. But ultimately, WASI isn't just defined by me making changes in my editor here. What's going to happen here is that all this stuff will present this to the WASI subgroup, and then these things will all get voted on. And the subgroup will have a chance to object if they think that forward is redundant with slice. If people think that, like, oh, you should just use splice and write your own loop, then that can happen. But for now, I think it makes sense to put it in and see how it goes. I think I've just been convinced at this moment. So forward is a function that takes this is a method of a resource. We don't need to have an output stream here, and we don't need a length. We just want to forward the entire thing. So there's just one argument. That's kind of simple. We'll return you the number of bytes that we read, but we don't even need a tuple because it's going to read to the end anyway. So it's just a U64. All right, pretty simple. I like how simple it is. Just a single argument. So forward is a method of output stream. So it'll take an output stream, take an input stream, and copy from the input stream into the output stream, and then tell you how many bytes it copied. Super simple. I like it. Okay. Let's see if I can keep up my comments here. Use case of splice where you don't know when, but you want to provide full stream type. As we just did. So since stream is sync, I don't think it's practical real world problem to have. Traverse error. Should be whatever is an allocation problem. Yeah, I think that's likely. I think we'll just kind of, allocation errors aren't friendly to recover from in any case. But I think that's sort of the nature of allocators and this kind of design. People should just use readable size buffers and they won't hit the problem. That's an oversimplified way of putting it. I think there's more nuance we can add to that, but I think that's kind of the general direction we'll head in. How do we compare this with Virtio virtual queue? I myself am actually not familiar with the Virtio virtual queue API. So if anyone knows about the Virtio stuff and can tell me how this kind of corresponds, that'd be really helpful. My source for a lot of the stream API design stuff is looking at Unix streams, also looking at streams in Rust, Java, C# kinds of languages. So looking at like the programming language standard library kind of perspective of streams, not necessarily the system like VM level streaming. So my guess is that things should map pretty well because it's a pretty pure concept of a stream. But T is an interesting question. Sorry, I'm getting ahead here. Back with the zero case. Let me get to T. Let me work through the questions in order here. Let me get to T. If I read document 0, flat 0 represents a request to 0 bytes, which should always succeed. Yeah, so if you're always succeed, because if it's the end of stream, reading 0 will detect the end of stream. And return empty list. Okay. And I should also mention that like my wordsmithing here on the fly is not the smoothest. I know phrases like this function returns and assuming the stream hasn't reached yet. You can imagine writing these things in a lot more sort of formal and precise language. I think there'll be time for that. I think right now I'm just hoping to like write down the intent and get things documented for what we intend, and really just take this opportunity to like review the design, so that in the future when we have the people who have more expertise in writing formal languages and writing precise documentation than me can come along and clean this up. It's kind of the perspective. Okay, how do you detect errors? Okay, zero case repeated, providing list U8 instead of U8. So you want repeated that could write the same list over and over again. That's an interesting point. I think my sense is that that's like I don't actually have any like use cases in mind for that, either in the present system or in sort of the generalization to built-in stream types in the future. So we could do that. I think there's not really anything preventing that, but I think that's just less interesting. It's also getting a little bit tricky because if the write of list U8 fails or gets interrupted partway through a list, we would want to have a way of telling you how many bytes it wrote. Like you got an incomplete number of lists written, which is kind of an awkward special case. So I think my on-the-fly instinct is that that's not something we need to have. But if people have use cases for it, we can certainly consider it. Block could be an arg. So blocking, are you talking about like async versus sync when you say that? I think the answer there is like we're definitely thinking about async. That's definitely part of the thing that we're thinking about. And the vision is like we want the stream to have a built-in kind of concept of async, and an idea is that it should work even for languages like if you're writing in C and expecting POSIX community or POSIX semantics of blocking, we can implement blocking semantics on top of async streams by essentially having your task, request a an async write, and then in something like the libc or like the standard library for your language would implement blocking semantics by immediately blocking on that async stream. And so the idea is that like async will be built in, and then people who want to have like call a read without blocking can say like, I'm not going to use my standard library, but it's built in for like the sync operation. I'm just going to call the async version directly, or I'm going to use.
Live streaming is on.
Okay, it appears that I got bumped off of live streaming.
Live streaming is on.
Yeah, I try to figure out the streaming thing here. I don't actually know if I'm online right now, but I'm.
Live streaming is on.
Okay, I think I hit. There's some software involved here has maybe like an hour timeout on it, so I think I hit that. Apologize for that. I think we're back, or maybe I'm back now. So I think some software involved. We hit about an hour mark in the talk, and that's when things disconnected. So I think that might be what we're hitting. So I'm working through the questions here. We got a lot of great questions. Let's keep going here. What assumption on buffering the data, written, splice, and forward can it be documented to be flushed? This is a lot of great content, and I'm sort of wondering if like maybe we need to spend more time on streams in a different forum, but I will attempt my best to cover things really quick. So this API has no concept of flushing buffers. There's kind of no concept of buffer flushing going on. It's just like there's a stream. And I think for most use cases, like imagine like a pipeline of A is pipe to B, pipe to C kind of things. You typically don't need to have like explicit stream flushing directives going on in the middle of that pipeline. And hopefully we're back here online. Hopefully people are back here. I'm going to put this in the chat, just make sure people hear you say this. Okay, so in fact, I should actually go through these questions again when I have more time. I think on the live stream, I'm kind of like trying to do my best to answer these on the fly, but these actually deserve kind of more in-depth answers. So maybe we'll come back to these. Forward and T. T again is kind of complicated because this is a blocking kind of situation, and if you have a problem where like if there's two readers, maybe one of them is going to block and starve the other one. So T is kind of a complicated thing to do right. I think there'll be ways to do a T in the async model. And in fact, if you watch some of the async presentations, I should drop in this slide presentation here. People that are interested in sort of the full vision for streams, I'm going to drop a URL in here. That's a link that's a presentation that was given to the WASI Circle group a while ago about kind of the vision for the point model async model, and that has in part of it has an explanation of how T would work. So T is kind of part of the story. I think right now it makes sense to leave T out, at least for now. It'll be something we can consider later, but the blocking issues make it kind of complex to think about. So I think we're gonna push T in the future where we actually have an async model. We can deal with things like blocking and keeping running when some things are blocking in a more structured way. Verdeo virtual queue is a ring buffer to switch shared memory of data on this ring buffer between host and guest. I'm guessing similar thing could be used here in WASM. I think so. Again, this is also going to be an answer that I'm going to push on to building the stream model in. So if you look at the read function that's in this API, if we go take a look at that, you'll see that this read function returns a list, and people who are really going to look at optimizing heavily are not going to be happy with this, because what returning a list will effectively mean is that every time you do a read, we're going to do a dynamic allocation to allocate memory for that list, and then when we're done with that list, you're going to free it. And so doing an allocation on every single read function is not going to make people who are really trying to optimize happy. But then I think this is kind of like represents like the best we can do for now, or at least without having a significant more complexity, and without having to go into like actual shared memory immutability, which will break some of the important properties of the component model. But I think in the future, what we can imagine is when we build streams into the IDL, they can have much better integration with the source language, and we can avoid having to have like, allocate a list, which you could think of as like a Rust vec or like a similar kind of data structure, or basically calling malloc to allocate the memory for this list. So in the future, with the actual built-in streams, that's a thing that can go away. And then, in fact, with the async model, one of the kind of out there ideas is the async model. Actually, if you look at the slides I presented, there's a lot of stuff in there that's very similar to IOU ring. And the hope is that eventually we could run the async model directly on top of IOU ring and use IOU ring complete with the OS writing data directly into user space buffers in the WASM code directly without any extra copying. So like another part of the zero copy story is if you're talking to the host can zero copy into your buffers without any extra work. Like it can just like write the data directly there instead of writing into a separate buffer and copying it in. So I think this is also a thing where in the future with built-in stream types, we'll be able to do much better language bindings that can give you much better I/O without having to do this allocation. Is IOU equivalent for WASI something that would be in the async API? Yes, that's definitely the vision. So that async presentation I just linked to there, that kind of lays out this vision for how async can work in the system and be integrated with different languages. And it's designed very much with IOU ring in mind. If something similar to put in our company, we are thinking of making an open source project and contribute back to the community. That's cool. We can discuss this. Okay. Guess for time for browser deploying WASI, capable of running WASI. So browser support is not something that's currently on anyone's immediate timeline for WASI. The basic shape of this is that what we'll probably do is WASI right now is focusing on the non-web, non-browser kinds of use cases, edge compute, cloud compute kinds of things. I think that's where WASI is going to initially. That's where we are initially focusing on. That's where it's going to get its initial adoption. And a big thing with WASI is that, like, in order for this to be usable broadly, we need to build up a lot of tooling, a lot of better documentation. This live stream today is one small part of what will be a much bigger effort to have documentation for all this stuff and tooling and libraries and package registry. There's lots of pieces to make this whole thing work. And I think on the web, it will make a lot more sense to talk about doing WASI on the web when a lot of these other pieces are in place. So right now, if we go to the web and say, like, let's do all this stuff, the story for web developers will be like, you're going to do a lot of stuff and deal with a lot of unstable tools, and you're going to get an overall experience which is worse than you can get with your existing tools. And that's not really a great, compelling story for anyone right now. So I think the answer is, like, let's wait until the component model gets more developed, get the tools get better, better documentation and more libraries that are out there, more things that can, more languages can work directly with this. And then when we start looking at, okay, now does it make sense to do this in the browser? I think we'll be able to tell a much more compelling story. I think that's when the component model's strengths, like the shared nothing model, mutually untrusting components, composability, all those things will start to shine, and they'll be more worthwhile in a situation where you can deploy these things and the tools work. So I think there's no immediate timeline for that for browser support, but I'm former Mozilla. A lot of people who work in the component model are former Mozilla, And so we have connections to the web world. We're talking with people in the web world on a regular basis. And so we're all connected. I believe that WebAssembly is a single ecosystem. There's not really a split between web and non-web. It sort of looks like it because with WASI focusing on non-web stuff, it sort of looks like we're going off that direction. But I do think there's a path by which these things can unify. That might mean that things like WASI file system might not be a thing that ever makes sense in browsers, or it might. There's actually pushes in the browser space to push towards having more file system-y things and maybe even more blocking I/O things. So we'll see how far that goes. But one of the cool things about WASI is that all APIs are virtualizable. And so even if we have things like WASI file system, even if that becomes an important API in the ecosystem, we can virtualize that. We can decide what is a file system, what does a file mean, and it could be, it could mean many different things. It could be even in a browser context, a file could mean different things. It could mean you're talking to a host, something on the user's drive outside the browser, or you're talking to an IndexedDB backend, or you're talking to an in-memory file system. There's a lot of different options for what this could end up looking like. And so this is all kind of like future stuff. There's not much out there in the space of like immediate plans for browser things. So I think I've worked through the comment queue. Are people still connected? Are people still online? Can we still hear me? Did the reconnect work? All right. I hope we're online. The software here is telling me that we're still online, so I'm going to proceed on the assumption that we're still online. And get back to API. So we added forward. And okay. So that's the end of the Squid API. Let's go and sync this up to GitHub. I'll push this upstream to main. It's all done live. And I will put this together into a PR. So this is going to getting pushed up to my personal fork of the proposal repo. I will form this into a more official PR, which will get posted, and then people can comment on that if they want to. So that's the process is going to be there. So for now, let's just push that up. If anyone wants to see that live, the link for where I just push that to is here. And let's go to the next file. Put a file from GitHub. So one more thing on WASI IO, main branch. We're going to take a look at the README file. All right. This README file is the landing page. So WASI IO is technically in phase 2 still. Okay. If you want to see the proposals, the full list of WASI proposals, by the way, it's here. If you want to make a new proposal yourself, you can go to the WASI subgroup and talk to folks there. And that's the process there. So WASI IO is in there. It's in phase 2. So we're going to leave this. What did I do? I want to quickly check WASI clocks API. No, I want to check WASI clocks. So I'm just going to try to be consistent about how we describe this. Phase 2 is a link here. Okay, it's a link to that. So if we jump back to WASI IO, phase 2 a link, and champions WASI IO is now posted. So yeah, WASI IO was actually created before before we had this process in place, and so we don't have the phase 4 advancement criteria. We'll have to propose this and propose this for the WASI subgroup to get it approved. I'm expecting though that WASI IO's criteria will be something like, we want to make sure it works well on files. Sockets, pipes, sort of, if we do those three, yeah, I'm very much cognizant of not wanting to specialize WASI too much for POSIX, but in this case, I think if we can implement the POSIX APIs on top of this, that sort of gives us a good feel that it'll work well in many different source languages. So kind of where that ends up there. Table of contents. Delete this here. As with we did yesterday, I'm going to leave the table of contents. We have a low tech setup here with, we don't get to have generated table of contents yet. I'll update that later. Introduction. So WASI IO, we didn't actually know what it was going to be before. We didn't have an introduction. So now I can introduce what WASI IO is. Some of this is copy and pasted content, so I'm going to update that as we go. So introduction, WASI IO. Quote these things. Upstream and outstream. So they're utility functions that are designed with the idea of optimizing in mind, but optimizing isn't really a fundamental part of the interface. All right, so I think that's all I need to say here. Sort of keep it simple. Goals. POSIX like file and socket APIs on top of streams. Support many different kinds of host streams, including files, sockets, pipes, character, devices, and maybe even things like, I'll just say more for now. There's more things out there. That's sort of like the POSIX-y kind of set of host devices, but I think in the fullness of time, we're going to be interested in streams for things like talking to databases, talking to HTTP streams, that kind of thing. But I'll just leave it sort of vague for now. Non-goals. So we're not doing async yet. We know that async is important, but we're going to do that more properly with async, component model async built into the language. Bindings. So other non-goals here. Bidirectional streams. It keeps the system so much simpler if we have each stream as a single direction instead of having to have a stream that can do both and have some kind of like dynamic like failure if you try to read to a writable stream or write to a readable stream. And now those can just be type errors. Bidirectional streams, and people have other ideas for non-goals that we talk through and add those. Okay, API walkthrough. And I'm going to do what I hope is a fairly simple thing here. Input stream. So I'm just like open code an example here. I don't even know if this will compile, but this is roughly what we're kind of envisioning. Some kind of function is going to process data. It's going to take input, which will be an input stream. And so the name of the input stream in WIT is input-stream. And it's lowercase and it's kebab case with a hyphen like that. What that means is that we can map this into source languages with whatever casing, underscores, camel case, whatever thing you've got that makes sense for the source language. So in Rust, types will be the sort of camel case with capital letters. And so it'll get mapped in like that. That'll be our input stream, which is the input stream from WIT. And maybe you have an output to write to. I'm going to be a little bit vague and not go into the error type just for now. We're just going to illustrate and typing Rust into a Markdown editor. Okay, we'll be a little bit vague here and not try to go into too much detail about exactly how this stuff will work. Or maybe we can just say this is going to it's going to bubble up the stream error. So the stream error from the library, we'll just bubble it up here because we're going to be boring. In a real situation, you could imagine mapping the stream error to an API-specific type that we define. In the standard library, it'll map these things to IO error, but that'll just be sort of layers on top to make it easier to use. And so we're going to read some data, a loop, and always use a random power of 2 for your buffer line. I don't expect people would actually write this code very often. Literally like this. This is just sort of taking some shortcuts to show off the API and how it works. So I'm going to do this. And we could just do question mark because we're just forwarding on the error type from the stream to our callers. So we could just do that. And actually, it's going to return data. And the bool is the end of stream. And so if we get data, this could also get interrupted. So we're going to have our loop around this. If we're going to do a live stream about coding, I probably wouldn't use this editor, but this works pretty well for Markdown stuff. So we're going to Yeah, I'm just debating how much detail should I go into. Actually, doing a copy loop here is kind of annoying because write could get interrupted. It could write fewer bytes than we requested. So we're going to have a view how much remaining data we have. Well, the remaining is not empty. So refile that. Okay. I don't know if this is actually correct, but it sort of looks like it's not too bad. And then if we reach the end of the stream, then we'll break and we won't bother doing another read. So this is actually copying things. It's just copying stuff, which is sort of the copying way. Copying from input to output using read write. And then copying from input to output. And so here we're going to use splice. It's a little bit simpler. So we're going to do splice takes size to copy, and we're going to do just give me the whole thing as much as you can. Might fail. Let's oopsies. So good to look at. Splice does return a bool. Really good. So it's going to return copied in the stream, and in this case, we don't actually care about the number copied. The signature is written. We're not going to return the number of bytes written, so we're just going to do that, and then we can skip all this stuff, and we just say copy as much as you can. Get to the end of the stream, then we're done. And that's it. In another use case, using forward, code quote this stuff because that's good. So we're going to copy with forward. And now we don't even need a buffer len. That goes away entirely. We just say loop goes away. This should also have okay. Yeah. Okay, so these are some pretty simple examples kind of showing off the basic use case of the API. Read and write, you get do a bunch of stuff here. I think so this is a little bit ugly. I'm not super happy with how this looks, but I think it's going to get significantly better when we have stream built into the language in async timeframe. And I think it's also going to be the case that a lot of user code won't be writing code kind of at this level. It'll be using code at like the level of standard libraries that'll have copy functions that will do this under the covers. And this is simpler. It still sort of knows about, oh, actually we can delete the buffer line. We don't even need that here, which is nice. Oopsie, I gotta edit the edit window, not the display window. And copy the bytes through. And then the very simplest version, we're just going to forward the data on and like do it all for me. Might fail, that's okay. And then succeed. Okay, detailed design discussion. So I may have to do this offline. I'm actually taking more time to do this proposal than I could have imagined. So I may have to do some more writing offline here. Which might be a good idea because I might want to like take some more time to sort of digest the feedback we got here today. But let's see. Design choice 1. So actually, there's more to it than there's more going on here than just this. I think if we have a socket which is in non-blocking mode, that's a thing we should be able to deal with in WASI Preview2 timeframe. I think when we get to the WASI document proposal, we're going to want to take a look at that and think, okay, there should be a way to do non-blocking I/O, and it won't be the super fanciest async model. It'll be that like you can do pull one off. At least for now, that's what we'll have, and you should be able to do non-blocking I/O with that. Yeah, I think thinking about this in the context of sockets, actually, I'm sort of going back on this. We maybe should have more to say here. What this might look like is we say that if you're reading from a socket and you get E woodblock from socket API, that just turns into a short read. Like there's just not enough bytes there, maybe. I'm trying to think about ways to preserve the generic stream encapsulations, that we don't have consumers of streams being aware of the producers of the streams, being aware of like, oh, this stream's in non-blocking mode or not blocking mode. And so it might be enough to say the stream can just return a short read. And so like the use case would be like you've got your poll going on. Your poll says, okay, these events, these streams are ready to read from, and then you go ahead and do the read, and then the read can return however many bytes it can do at that time, and then you should return and do a poll before trying to do any more reading. That might be how we end up having to model these things. I'm going to document that for now. That may be something I'll have to come back and revisit. Okay. Why do they use these store sizes? And Okay, I'm going to delete this considered alternative section. I don't think we have anything to say there yet. Let me just double check the stream here. There are a lot of good questions here. I'm wondering which of these can be forwarded in here. Document this. Okay. Forward. Okay. Yeah, we'll need to write more about this here. Interested in feedback. Yeah. So if things go well, we'll use streams for everything. The streams will be sort of the key vocabulary which we make a lot of things connect to each other. Definitely lots of people are interested in streams. Let's see. I don't have any names of people who have worked with this too much. We got a lot of feedback from Luke Wagner working on the component model. I've talked with him directly about this API in a lot of ways. I could acknowledge the forward function is a good idea. All right, if I've missed anyone, I will attempt to go back and fix that. But for now, this is what we have. And that is it for WASI.io. So I'm going to upload this to GitHub. Push to main. We are live. All right, so that WASI.io link I put above, that's where this is going to. I will turn these into Power PRs later. So next question is WASI poll. We have about 20 minutes left in this stream for WASI poll, and we'll see how that goes. Which actually kind of good because WASI poll is kind of in a place where we don't have a lot to do yet. So put a file from GitHub, or it's going to need a lot of sort of pretty heavy-handed editing because currently, as you'll see, the WASI poll.with.md file is still very much based on the Preview1 poll API. It looks a lot like the Preview1 poll one-off function. And so it's got the same subscription, and it's a struct. We turned the union into a variant here, which is like a nicer thing than like a union. And so the types here are a bit nicer, but it's still basically the same idea. We have the same kind of subscription events and coming out events. And read event still returns the number of bytes. In this copy of the API, write event still returns the number of bytes. And we have some of the stuff has been duplicated because we don't have facilities in WIT for importing types yet, but that's actually showing up in the tooling as we speak. So that's coming up. Fix the syntax here. But I do want to show on the stream Preview2 prototyping. So this is a repo that I and others are working on to prototype all these APIs. And so these APIs, I've been working to keep these in sync with the official WASI proposal repo APIs. But poll is actually a case where we had to evolve this a whole bunch, and this differs quite a lot from what you see in poll one-off function. And so let's pull up this poll API. Can we view this? Let's do the raw view here. Make sure this is on camera. We'll zoom in a little bit, make it bigger so people see this. So this is the poll API. There's work to be done here to integrate this, but I'm going to take some time here to talk through what this is and maybe write some documentation and think about the design while we're doing this. So the WASI poll API is designed around this idea of feature. And actually, this feature even is some of a misnomer, and we might rename this in this API. But basically, the idea of what we're doing here is we're factoring out the concept of a waitable thing. In fact, waitable might be a better name for this. It's a waitable thing, which will be, in this case, it's a resource. This is all in anticipation of the actual component model giving us actual features as an actual type in the like a built-in type, just like streams. So streams and features are like built-in types that we want to have. But for now, we're doing like pseudo features and pseudo streams as resources. And so what this is a way of like factoring out the concept of I want to wait for this thing from what the thing is. And so instead of saying we're going to have a poll API that has a subscription variant that knows how to subscribe to a clock or a stream, we're going to say a clock has a way to give me a waitable handle, or a stream has a way to give me a waitable handle. It's going to be this what's currently called WASI feature here, but it'll be named to waitable probably. And then when we do this, then we can have the poll function. So actually, I'll explain what's going on there later. But we can have a poll function. Here's the final poll one-off. It's very simple. It's a lot less like structs and result and event types going on. It's just like we got an input is a list of these waitable things. Like here's a bunch of things we want to wait on. It's all the same type. It's just WASI feature, which is just this handle to this thing, which sort of abstracts over the thing we're waiting over. So poll one will wait for those things. And then they'll give a list of U8. As the comment here says, that ideally should be a list of bool. But there's various tooling reasons why we're not doing list of bool right now. But conceptually, this is just a list of bool saying which of these waitable things was ready. I think we're actually going to iterate on this because I think there's potentially some information that we don't have that we might want coming out of this. Like in a Unix poll, you get information like, does the stream not just readable, but did it have an error? Is the information you get. But this is kind of the overall shape of it, of like, instead of having to have a subscription struct, the idea is to have just waitable handles and then say the poll one-off can just wait for any kind of waitable thing. And that actually makes it more accessible. Because with a subscription struct, the kind of poll API needs to like hard code, here's all the things that I could wait for. I could wait for clocks, I could wait for streams, input streams, output streams, and that's it. And if you want to add other things to wait for, basically they need to be like integrated into the poll API itself. And this kind of design is pushing us in a direction towards having a more open-ended poll system where you can say, we have other APIs that could do I/O, and they can have waitable things. And we want to have a poll that can wait for all waitable things, not have to have hard-coded the list of things you can wait for. That's kind of where this is going. In this version of the API, all this stream stuff, this is actually skip, write repeated, and splice. You can recognize these from the WASI I/O thing we were talking about before. In this prototype, they're currently in the poll API, which is not actually a great place for them to live. And so these will have to move out. And in fact, we will move this out to match the prototype with what's currently in the WASI IO repo. That'll be synced up. So kind of ignore all this stream stuff for now. Stream error, drop stream, drop feature. Ignore all that stuff for now. Really, the only thing that matter here is this feature type, which will be renamed to awaitable, and pull one off function. We just take a list of things and return the list of U8. And the interesting question is, should there be a list of not just like, is it readable, but is there an error? For a socket, you want to know if it's actually like there's nothing ready yet, or is it actually an error, like a hang up on the other side? So no one has asked any questions in the last several minutes. I'm getting a little bit nervous that we're actually not online at this point. Hopefully we are. My live stream tells us we are. It tells us we have 5 people listening. So if you are listening, please comment. I've had a few disconnects, and I've had a few times where I've been talking to the void. So please comment with questions. One other thing I can mention here while we're looking at the poll API online here is that the one-off in the name poll one-off, that's in Preview 1 as well. That comes from the idea that like we know that this is a sort of old style poll function. This is kind of like the ye old Unix poll function, which you give it a list of things to poll for, and every time you call it, it has to iterate through that list, which means it's not very scalable. If you want to do this over and over again with many thousands of events, you're going to waste a lot of CPU time scanning through those events to find out which ones had I/O to be ready. And so we know that's not very scalable. Modern OSs go beyond POSIX, and they have things like ePoll in Linux, KQs. Windows has a way of doing this kind of polling as well, but they're all a little bit different. There's not really like a single way to do this. And then even more modern times, we have things like IOU ring coming up, and IOU ring is now in Linux. It's also now in Windows, and it's kind of this additional way of looking at waiting for many events at once and doing IO. And so like poll one-off is definitely not intended to be like the last answer for how to do polling. There's definitely a need to do more than this. But I think that the design intent here is that we want to do something simple. All these other APIs get much more complex, especially when we want to start talking about cross-platform abstractions and how this is going to work. And so poll one-off is nice because it's very simple, and it will hopefully be enough to kind of get us to the point where we can do proper async. And the async model, I looked at the slides to it above here. One model async report has a concept of a wait built into it, and that wait essentially will be like the IOU ring style wait. And so more improved kind of scalable polling will be in the cards here. But there's kind of this question of like, what should we do now in this moment today? And my proposal is to keep it simple and to stay with poll one-off, which is a very, very simple function, especially when we reduce it down to, we factored out blockable things from the things they're being blocked on. And so the API, if we ignore all this other stuff in this API, there's just one function, just like poll, here's a list of things to wait for, tell me which things are ready, and that's it. That's the only thing you have to know about. And that's something that we can easily implement on many different platforms. We have an implementation that's working on Unix and Windows in this prototype repo, and it works pretty well, even if it isn't the most scalable thing for the long term. So that's where we're at here at WASI Poll. I think the main work here is to synchronize this poll thing with what's upstream in the WASI Poll repo, which basically replace the contents of the old poll one-off based on explicit subscription struct and variants of the things they can wait for with this new pollable concept. And so now, in fact, just within the last day, the WIT bindgen tooling now has support for use statements, and we're able to share type between one WIT file and another WIT file. And so I'm hoping to take advantage of that just landed to split these things up and to then redo the poll API with this ability to share types. So with that done, I'm going to finish up the stream here, and we'll resume tomorrow. So today we got through WASI IO, and we got through WASI Poll. We talked through WASI Poll. There's more work to be done here, but we talked through it. And then tomorrow on the stream, we'll dive right into WASI file system and WASI sockets. That might be too much for. I have a 2-hour slot booked up for these streams. I don't know if that's going to be enough time to get through the whole thing. So there might have to be more streams coming up. WASI sockets might have to get bumped to a later stream. we'll see how that goes. I'll have to schedule that stream sometime. So that's all we have for today. Thanks everyone for showing up. Thanks for the great questions. We had a lot of great questions in the stream. It's really great. Feel free to reach out. I'm on Mastodon, WebAssembly Discord, my code Alliance Zulip. You can find me around various places. Feel free to reach out anytime, ask me questions, and thanks for watching the stream. Hope you can show up for tomorrow's stream as well. And that's it. Bye.